So we're going to be using dimensional analysis and moles for a long portion of this class. I highly suggest you go back and rewatch the videos or come for tutorials, because you need to know how to be able to do this. If I tell you, for example, 5 grams of water, 2 molecules, and water has a molar mass of 18 grams per mole. Personally, I can't do these problems without the grid and writing all the numbers. It's just too easy to make stupid mistakes. You should begin with the number they give you, 5 grams. And then I'm going to add a conversion factor. And I know that here is a conversion factor, 18 grams to moles. So I would put in, because grams is here, I would need to put the 18, so this is 18 grams per 1 mole. So I know the 18 grams would have to go on bottom, and the 1 mole, still working? Another stapler over there. So I know the grams has to go on bottom to cancel out the grams here. One of the number 1 issues I saw on this homework is people do something like this. They would put 5 grams, and then they would come over here and do 6.022 times 10 to the 23, 1 mole. Let's look at the units on this. This number right here is molecules. So we have a gram times a molecule divided by a mole. The grams and the moles didn't cancel out, so this obviously isn't the full answer. You need to be putting the units in the grid and seeing if what cancels out. A gram divided by a gram canceled out, so now I'm in moles. Moles is not molecules, so I need to add another conversion factor. So I know the ratio of 6.022 times 10 to the 23 molecules per mole, and the mole needs to be on the bottom, so I put mole on the bottom. I put 6.022 times 10 to the 23 molecules on top. Then I cross out my units. Mole and a mole cancel each other out. The unit I'm left with is molecules. You got them wrong because you didn't come up with the right number. Like, you did it completely wrong. If you had, like, if you came up with a number, I got it right. I took off a point if you got the number wrong. But if the number was right, you got it right. If the number was wrong, you got the whole problem wrong. Another example is converting moles. So converting moles to grams. Some people would do like 5 moles to grams. They do 5 mole. And then they come over here and put 6.022 times 10 to the 23 over 1 mole. Yes, mole cancels out, but what unit should be attached to 6.022? Atoms, or molecules. not grams. This is the counting number that tells you how many atoms are in a mole or how many molecules are in a mole. But anyway, I'm moving on today. I highly suggest you go back and review or come for tutorials because we're going to be using this quite a lot. So, before we go into gas laws, our main unit this time is going to be over the gas laws. Before we do gas laws, we need to understand kinetic molecular theory. So by the end of this lecture, you should be able to describe the assumptions or rules of kinetic molecular theory, also called KMT. Only thing you need to write here is kinetic molecular theory equals KMT. So, energy. Energy is defined in science as the ability to do work. So if you have energy, you're able to do some work. Work in science is mathematical. It's technically equal to force times distance, but we're not going to really get in there. All you need to know is work is something that is done that causes motion, or really just need to know that energy is defined as the ability to do some work. In a system, the total energy of an oscillated system remains constant. So this is known as the law of conservation of energy. The total energy of an isolated system will remain constant. If I go too fast, tell me to stop. So potential energy is stored energy due to its position or configuration. Put that to the end of this, or configuration. For example, if you compress a spring, technically you are moving the position of the endpoint of one spring. You're adding energy to that, potential energy to that spring. Bless you. If you drive up a hill, you're adding gravitational potential energy, which means the car has the ability to roll down a hill after it gets to the top. Kinetic energy is energy due to motion. So it's the energy of motion. I would also write this for potential energy. Gravitational, you don't really need to know gravitational because we don't use gravity in this class. But it's mgh is the equation. Kinetic energy, we will use this a few times, is equal to 1/2 mv squared. 1/2 times mass times velocity squared. This will get important whenever we're talking about temperature because of movement. I think there's only 1 or 2 questions in the entire year that you have to use that equation. I think only once, actually. So, particles in solid, liquid, and gases. again, the main unit that we're going to be looking at is gases. So we have solid. Solid, the atoms are really strongly bonded together. Liquids, they're loosely bonded, but there are still attractive forces between them. And then we have gases, where the particles are not bonded at all. So solids make up a bunch of particles, atoms, or molecules that are packed tight. And unfortunately, this PowerPoint's really screwed up. It's a really old PowerPoint. You can see the solid on the picture is kind of hovering over the word move. And unfortunately, I couldn't edit it. So do you think that the particles have high or low kinetic energy? So if I were to, so remember, energy, kinetic energy is movement. So if I were to cram all y'all into that closet, how much would y'all move around? Versus if I let y'all go out in the field and be sprinting and running. It'd be low kinetic energy. The particles are unable to move around. They're stuck. Think about the atoms in the very middle of that block. They're unable to move at all because they're being compressed by all the other atoms. So is there much room to move? No. And also, it says low kinetic energy at the bottom. Liquids are also made up of atoms or molecules that are still locked onto the neighbors, but more room to move. They have more kinetic energy than solids. So they're able to move and slide past each other, but they can't really move that fast. Because they're constantly hitting each other or constantly being caught or pulled by other atoms. So you could think of this as like people walking down a tightly packed, like the mall. There's a lot of people. They're constantly bumping in or unable to run at full speed because there are just too many people in the way. And then we have gases. There are tons of rooms, so a lot of kinetic energy. The average speed of the particles in this container is approximately 1,000 miles per hour. By the way, did y'all know that the air molecules in the air are moving at about 1,000 miles an hour? That means that if you are if you spray some perfume in the cafeteria, it could reach the gym and quicker than you snap, or about the time you can snap your fingers. Any guesses as to why you can't smell perfume from the cafeteria in the gym instantly? That's because there is a lot of particles in the air. The perfume will hit another air molecule and bounce backwards, so they zigzag back and forth. So they're constantly colliding with each other and other things, even though they're far apart. It's just so many particles in the air. Remember, there is 6.022 times 10 to the 23 particles in 1 mole of air. So they do move at crazy high speed. In order to investigate these phases, we're going to have to establish some rules. These especially to the gases, write down the red definitions and take notes as needed. How much notes you take is entirely up to you. If I go too fast, I may go back. So, rule 1. Gases consist of small particles that are very, very, very far apart relative to their size. So gas particles are teeny tiny. the particles that you've seen on your screen are huge. If gas particles were the size of a marble, the container that's been shown would have been the size of a football stadium. So if I go back to this picture right here, if that was the actual size, the container would have actually been the size of a football stadium, and them atoms would have been tiny marbles. So imagine that if you had like a big stadium, and you put randomly in it about 5 to 10 marbles, the separation of the marbles is about the size distance relative to each other. So we assume that the particles and molecules are super tiny and far apart relative to their size. So gas particles are always far apart. Gas particles are in constant random motion. The moving particles are constantly colliding with each other and with the walls of the container. So gas particles are always moving with random motion. They're constantly moving. They never stop moving. But they're also hitting each other, so they're constantly moving in random directions. You can think of them like bouncing balls that never lose their energy, or 3-year-olds at a birthday party. Collisions between other gas particles and the container are elastic collisions. Oh. So repeat that again? So, say you have water. Mm-hmm. No. We'll get to that in a second. Temperature is purely kinetic energy. So it's at some temperature, and you're adding more temperature to it. So you're going from you're moving some kinetic energy of the gas, so the fire it has some it. So you're taking some temperature from the gas to the flame and adding it to the water. So it's just a transfer of kinetic energy from one place to another. So collisions between other gas particles and a container are elastic collisions. Collisions of particles are elastic. Does anyone know what this means? Kinda. So, this is more physics. So if you were to think of billiard balls. So a billiard ball, when one billiard ball hits another billiard ball, their speed is transferred between each other and they go off in random directions. We'd say that's an elastic collision because energy is conserved. Now think you dropped spaghetti onto the floor. The spaghetti sticks to the floor. That is an inelastic collision. Versus billiard balls. Or think of dribbling a basketball is elastic. Yes. So it's not a perfect elastic because there is some energy loss to the ground, so it won't go back up. But you can think of a basketball as very elastic too. An example, so dropping Play-Doh, it might bounce up if you throw it hard enough, but most of the energy is going to actually be converted into thermal energy, heating it up, and not bounce. So an elastic collision is one in which the entire energy is conserved as kinetic energy and not transferred into thermal energy or sound. No. The total momentum at before and after stays. So collisions between other gas particles. So did it bounce? Not elastic. Two kids in a bubble suit running together, they bounce off of each other, is elastic. So the energy isn't wasted, it only changes direction. Gas particles are elastic. So you can have, for example, so you can have one particle be going 10 miles an hour and another particle be going 5 miles an hour. And they hit each other. You can call one of them will, so the total speed between them is 20. One can speed up to 19 miles an hour, and the other one can slow down to 1 mile an hour, but the speeds are conserved. That's what it means to be elastic. It's really not speed, it's momentum. The momentum stays as momentum and isn't converted into temperature or thermal energy or sound. So there are no force or attraction or repulsion between gas particles. So we assume that they're not going to be sticking or bonding to each other. They're freely able to move. They might bounce on each other, but they're not going to stick to each other. So water likes to bond to each other. So if you take some water droplets, take a mist of water and point it at a surface, the water goes clean to that surface. It might not even drop down because it has a high surface tension. We assume gas particles, like if you blow air across your hand, you wouldn't be able to see a cloud of air sticking to your hand. It's just going to bounce off your hand or move past it. So waters like to bead up and bond. So we assume no attraction or repulsive between particles. So they'll always just bounce. There won't be any pull or bonding between them. The most important thing is what you were kind of getting at here in this. Everyone good? The most important rule of all is the average kinetic energy is dependent on temperature of the gas particles. The hotter the material, the faster the molecules are moving on average. So average kinetic energy depends on temperature. Another way of writing this is temperature is equal to the average kinetic energy of all the molecules. Now, so we have one equation for, let me probably draw this out. So this is true for everything. Everyone good? So let's say we have a solid. The temperature of this solid, so these atoms are bonded together. They're not going to move that much. But this atom is going to try to pull away, but these atoms are pulling it back together. So what you see is that these atoms vibrate in place. So they're constantly moving back and forth. They're constantly jiggling. And because they're constantly moving, the temperature of the solid is equal to the average kinetic energy of the jiggles. How much they're moving back and forth. For gas molecules, let's say we have steam, it's mostly going to be on how fast it's moving. So we take the mass of this, its kinetic energy will be equal to 1/2 times its mass times its velocity squared. That's mostly is all of its kinetic energy. There will be a little bit of vibration between the molecules that will add together, but overall, this is the main equation for that. And like I said, I'm only going to ask this question one time in a year, and I'll tell you which problem it is, and I'll remind you what the equation is. So, no. For the most part, we don't really care about what the kinetic energy is. We care about temperature. So I'll just tell you the temperature of the average kinetic energy. It's too complicated to add up 6 times 10 to the 23 particles, because they're all going in a random direction. We just take the average and call it temperature. But if you go from a solid to a gas, so this is a solid, this is a gas, what you're doing is heating this up to give this enough energy that it can fly out. Yes. Yes. And when you convert to a liquid, it just so happens that the forces aren't that strong enough. The forces pulling together somewhat pull it so that it doesn't escape into the air. But there's still enough kinetic energy that they'll slip and slide past each other. So that's the reason why heating up ice causes it to melt. You're increasing the kinetic energy, and you start having the water molecules move past each other. So the code word is on the screen. And I should be able to see the code word, and thank you for reminding me. So, measurement of coldness or hotness is due to energy. So a temperature really is a measure of energy. Somewhat. There's a difference between temperature and heat we'll get to later in the class. We have something known as absolute temperature. It's measured in a unit called kelvins. Note that kelvins has no degree symbol. Again, we're using the metric system. Metric has Celsius. And note this PowerPoint is wrong. Or I should say the PowerPoint rounds. I like at least 4 significant figures. So we will use the exact number here. It's 273.15. So to convert from between degrees Celsius to Kelvin, add 273.15. From Kelvin to degrees Celsius, you subtract 273.15. So make sure that you make note that the conversion factors to add or subtract 273.15. Now, we're only going to be dealing with Celsius or Kelvin. Fahrenheit, we don't have to convert between it because we will not use Fahrenheit in this class. Note that the Kelvin and Celsius degree Celsius scale are the exact same. It's just that Kelvin has been slid down to include absolute zero. So Kelvin begins at absolute zero at 0 Kelvin, whereas Celsius begins at the freezing point of water at 0 degrees Celsius. That's the only difference between Celsius and Kelvin is where they start. So 1 degree Kelvin, like a change in 1 degree Kelvin, is equal to a change in degrees Celsius. So for example, the freezing point of water is 0 degrees Celsius. And if you were to heat it up by 1 degree Celsius, it'll be equal to that. To convert this into Kelvin, we would add 273.15 Kelvin, and we'd add it here, 273.15 Kelvin added. So this is 0 degrees, is the same thing as 273.15 Kelvin. 1 degree is the same thing as 273.15 4.15 Kelvin. So the change in temperature here is 1 degree Celsius. The change in temperature here is 1 Kelvin. So change in temperature is the same. I could have done this 0 to 10, or 273.15 to 284.15, the change in temperature. By the way, I assume most of you have never seen this notation. This is not a triangle. This is the Greek letter delta, equivalent to our Latin letter D. It means change in. So change in temperature is 1 degree Celsius. Change in temperature. Another way, so if you have delta T, that's the same thing as final temperature minus initial temperature. I do use this a lot in the class whenever I'm writing, because it's better than doing final minus initial or writing the word change in. So, for example, going from 20 degrees Celsius to 35 degrees Celsius, that's the same thing as going 293.15 Kelvin, because you add 273.15. And we add 273.15. So that would be 308.15 Kelvin, right? And so the change in temperature is 15 degrees Celsius, or you can say the change in temperature is 15 Kelvin. The reason why I'm bringing this up is that in the later when we start dealing with gas laws, we're going to have an equation that will look something like NR delta T. This is change in temperature. Does temperature need to be in Celsius or Kelvin? But remember that change in temperature always gives you the same value whether or not you're in Celsius or Kelvin. So anywhere we have a change in temperature, it won't matter if we're in Kelvin or degrees Celsius. So change in temperature, it doesn't matter if you use Kelvin or Celsius. So if you're finding delta T, it does not matter if you're in Celsius or Kelvin. The only time it matters is if I ask you to find final temperature. If I ask you to find final temperature and your initial temperature is in Celsius, your final temperature is going to be in Celsius. For the most part, it's required that you convert to Kelvin to do the math. So let me write that out. Let me go back, because that's important. If you plug a temperature into an equation and it's not change in temperature, you absolutely have to use Kelvin. Equations do not work unless it's in Kelvin. The only exception to this is that change in temperature is the same whether or not you're in Kelvin or Celsius. But if you have to directly plug in a single temperature, not a change in temperature, it has to be in Kelvin. If you just want to be safe and always convert to Kelvin, do that. But sometimes that's troublesome doing delta T's, so I usually keep delta T's in Celsius. But if you have to plug in a single temperature, it has. So if the equation was nRT, this T must be in Kelvin. Whereas nR delta T can use Kelvin or Celsius. So if it's T, must be Kelvin. Delta T, you can use Kelvin or Celsius. So nRT, we haven't learned it. It's ideal gas law. PV is equal to nRT. But we'll get to that tomorrow, I think. Probably not tomorrow. But if you have, for example, change in pressure times volume is equal to nR change in temperature. So a small bit, so a change in temperature will cause a change in pressure. Here we no longer need to worry about Kelvin. We can also use Celsius. So, for example, gallium is a metal that can melt in your hand at 302.93 Kelvin. What is the temperature in degrees Celsius? Yes. That'd be 29.78. It's 300 minus a number close to 300. So it's 300, somewhere as a number around 300 minus a number close to 300. You'd expect it to be close to zero. This a basket of chicken strips that you order at Raising Cane's is 77 degrees Celsius. What is this temperature at in Kelvin? So 350.15. I know. Oh. So absolute zero and Celsius is negative 273.15. So in Celsius is negative 273.5 degrees, 0.15 degrees Celsius. And Kelvin is zero. So standard temperature or standard temperature is going to be 0 degrees Celsius or 273.15 Kelvin. So if you see something called STP, you might write this. STP stands for standard temperature and pressure. It's an outdated system, but a lot of chemicals we like to compare each other, and we'll compare them at some standard. Because a lot of properties change based on temperature. You might know that some metals expand when they get hot. Bridges have to be built with cracks in them so that to allow for expansion. Different electrical properties depend on temperature. So we need some standard to measure against, and the first standard chosen was this one where temperature is 0 degrees Celsius. By the way, at absolute zero, it's the lowest possible temperature, all molecular motion stops. By the way, it is impossible to reach absolute zero. We've gotten to a billionth of a degree of Kelvin, but it is absolutely impossible to reach absolute zero. There are quantum fluctuations that cause motion to occur. Nothing can ever completely stop moving. There's going to be on a quantum level things moving around. Pressure. Pressure is equal to force divided by area. So if you distribute a force over a large area, it will reduce the pressure. By the way, I think it's, I forget these numbers, I use it every year. I think it's 100-pound woman in high heels. So if you do the math, if a 100-pound woman in high heels standing on one heel exerts the exact same amount of force as a 1-ton elephant on 1 foot. No, not on 1 foot. If an elephant sitting on 4s, one of his feet would be the equivalent of the force of 1 heel from a 100-pound woman. So a single spike, because you're taking a large force, 100 pounds of force, and applying it to a really small point. That is more than enough force to send the heel straight through your skull. Because you took a force and distributed it to a small area. How much time do we have? Standard pressure is 1 atmosphere. Also, it's the same thing as 760 millimeters of mercury, or 101.325 kilopascals. We will also be doing unit conversions between all 3 of these units. We will not stick to one standard unit of measure because it's not, everywhere you see, like for example, I have a vacuum gauge in there that's measured in atmospheres. A lot of science uses kilopascals. You usually get your blood taking in millimeters of mercury because they use mercury to measure it, or at least they used to. There is no standard unit for pressure. Technically, kilopascal is metric. We use a lot, so dimensional analysis to convert between them. It's also about the standard pressure in this room. I plan the lab to be Wednesday. I didn't get anywhere near as close as I wanted to today. It might be pushed off to Thursday, but depending on how much I can finish tomorrow.